Hi, this is Srihari, and today I'll be talking about modern interferometry. And basically, to talk about interferometry today, it's basically this technique which uses light and specifically interference of light to determine the distance or the surface roughness of any material which is given to us. It basically gives a very accurate measurements, and in today's times, being more and more used in modern machinery, as it gives very high precision basically results. So let's to understand this modern interferometry which is being used today, we need to go back a little bit and learn about interference of light. That is, I'll just be explaining that shortly to you.
So as we can see here in this diagram, there is this one source of light. Nowadays it's basically lasers, but before it was basically sodium lamps, and this travels through the single slit. So this is basically used to make it linear, to make the beam coming from this source linear. Then this basically travels through these two separate slits in phase. It's very important to remember that it's in here it's in phase, and the reason it travels through these two double slits is to make it basically to make it two separate beams, and these two separate beams go and hit this surface, and this interference pattern is obtained on the screen surface. And now when these two beams are in phase, that is when there is 0 degree angle difference between the two, we get constructive interference. That is, there is maximum intensity of light. And when there is these two superimpose, when there is 180-degree difference between the two, we get the least intensity, that is darkness, that is called the destructive interference. Now as we can see in this diagram, this part, that is the whitish part, is called constructive interference, and this dark fringe is the destructive interference. So like when we obtain this pattern on this screen, we can gauge the object from where the light is coming, and then determine the distance or the characteristic of the object depending on the interference pattern we obtain here. So that's basically the use of interference in this interferometry.
So we just saw the interference of light phenomenon, and the idea to use this phenomenon as a helping tool in meteorology, that is surface meteorology, was first thought out by Michelson Morley back in 1887. And they did this experiment to show the world that this could actually be done. Even though this experiment was actually a failure, it paved its way for further such inventions and products, which actually worked. And also, although this experiment principle is quite old, it's still used in interferometers today. So let's learn about this phenomenon.
So let us look at the setup of the Michelson-Morley experiment. Here I'll firstly explain all these parts to you, all the different parts required for the setup. So here we have this coherent light source. Nowadays, it's, as I said, it's lasers, but back then it was a sodium lamp. And here we have the interferometer, or also called as a beam splitter. Half of this is basically silvered, and the other half is this glass. So it's silver because it has to like reflect one half of the beam which is coming from here, and to reflect the other half, which is to the measurement mirror. Here it's the reference mirror, and this is the measurement mirror, as I said, and this is the detector to detect the oncoming combined rays or the beams. So from here the coherent light source, the oncoming ray comes in, hits the interferometer or the beam splitter, and half of this as it gets refracted reaches the measurement mirror, and the other half reaches the reference mirror. And reference from here, the reference mirror ray and the measurement mirror ray gets combined and hits the detector here. Now from here the interference pattern can be obtained, but also another interesting thing here is that depending the interference pattern in this thing depends on the angle this interferometer makes with the normal. If this is a perfect 45 degree, then there's a perfect circle interference pattern obtained. But if this is not a perfect 45 degree angle present here, then we obtain kind of like a helical or basically like a parabolic shapes in the detector, that is in the interference pattern. Also if basically this is not aligned properly, then we can't get the correct interference position in this detector. So it's also very important to like align this in the proper manner as given in the original setup. This is basically the original Michelson setup, and also now I'll explain to you how the other modern interferometers work based on this setup.
In today's times, there is a massive use of interferometry. It's basically used in a wide range of uses. It's also used in many different disciplines also, like astronomy and engineering and medicine, and even sometimes in telecommunications also. So like there are different types of interferometers available for different disciplines obviously, but let us take a look at one of the major ones. So as we know, we just studied the Michelson principle. One of the major ones interferometer being used today based on this principle is the Fourier transform interferometer. This basically is just very similar to the Michelson interferometer, the first one, but the only difference is that it's the one reference mirror moves translationally. So we basically get a clearer image, the clearer impression. So how does this happen is that as one mirror moves translationally, there are different images formed because from the same reference point, from the same material which is to be observed. So we get basically a spectrum of the images, which is much more, actually gives a much more accurate result as compared to when the mirror was stationary. So let us see one example of how this works. And also when we get these images, basically an interferogram is obtained. Basically there's a cyclic change in this interferogram, which we shall see how we can derive the results based on this interferogram. So I've written this quick equation for you, which is basically, I'll just show it to you. Here we can see that d is equal to lambda n by 2. So what is this d? D is the distance which is to be measured, that is the path difference, and lambda is the wavelength, and n is the number of fringes, the number of cyclic changes which is happening here in interferometry, and by 2 as we know. And so here let us assume that we're using a laser which has 633 nanometer, and number of fringes is obviously 1. And so like to obtain the path difference, d is equal to 633 by 2, which is 315 roughly. So we obtain the path difference like this, and thus the distance between the two reference mirrors is obtained, and thus our problem is solved to find the distance in this microscopic scale. So this is how one of the this is how a Fourier transform interferometer works. So there are other kinds of interferometers also, like a Newton interferometer, which is basically used to basically find the tomography of any object. It's more and more being used in medicine today, and I'll explain it to you how this can be achieved.
Let's take a look at this diagram. First, I'll explain all the parts to you. So here we have the light source, and here is the camera, which acts as a detector basically, and here is the illumination beam splitter, and this is the scanner. This rectangular thing is the scanner, and these are basically the lenses which is used to basically zoom in and to get a clearer image finally. And here is this is the reference mirror, and this is the interferometer beam splitter. And as you can see, in this type of interferometer, we get both these rays in the same direction. Therefore, it's also called as heterodyne interferometer. It's a category for them. And here is finally the object surface. And let us take a look at how the process works. Here we have the aperture stop, and as these two rays go, and they get magnified, and at the field stop and get zoomed, and they go to this lens, and finally the illumination beam splitter, where they travel to the pupil plane. From the pupil plane, they get diverged again, and then they go through the reference mirror and into the interferometer beam splitter, and they strike the object surface and then go back in the same direction as they came before till the illumination beam splitter, and then they go to the tube or zoom lens here, which basically again gives a zoom image to get a clearer perspective, and finally to the camera. So basically, if the object is basically flat, we get this kind of an image final hologram, and if it is basically kind of like has basically a texture, or is like basically rough, we get this distorted image. So based on the image obtained, we can judge the flatness of this specimen. So this is how basically Newton interferometer works to test the tomography, that is the flatness of this material given to us. Now let us learn about some other types of interferometers. The first one is the Twyman-Green interferometer, which is basically used to check the dimensions of optical components. Initially, only small components could be checked, as the light coherence value of this instrument was really small. And later it was upgraded, and the laser unequal path interferometer was created. This can now check the bigger optical components also, as the light coherence value is quite high. So next is a Michelson-Stiller interferometer, which basically checks the diameters of stars. The star Betelgeuse diameter was checked by Michelson by this device. Next is the LIGO for gravitational waves testing. The full form of LIGO is basically Laser Interferometric Gravitational Wave Observatory. It basically has a 4-kilometer arm. The next one we're going to study is Fabry-Perot interferometers, which is basically used in telecommunications. It has two thin mirrors, and an optical matter basically moves between them, and can only be worked when these two are in resonance. So it's quite used in the telecommunications industry. The other one is the Mach-Zander interferometer. This can basically check and graph the flow patterns in any tube or any tunnel. For example, like in a wind tunnel. This can be used in various disciplines such as aerodynamics, heat transfer, etc. The last one we're going to study is electron holography, which basically records electron movements in their interference. So a 3D image of the object can be mapped by using electron holography, which has a high magnification and a very clear image as compared to its peers. Now let us look at a real life example of the interferometer. This basically is the laser head from which the light beam comes out. This light beam has to be coherent and linear. It basically travels through all these mirrors, which are called the measurement beams, and these two are the stage mirrors. The one contains the mask and the other contains the wafer, which is basically the observation point. The sample is basically kept here, which is to be analyzed. And this is the real life image of a functioning interferometer. This is the laser by which the light beam comes out. These are the different mirrors, and this is the display board, which basically gives out the calculated wavelength or length or etc. etc. Last but not the least, let us see how errors creep up in this measurements of interferometry. Even though this interferometric results are very accurate and precise, but it still leads to some errors. The sources of error can be many, such as air temperature, humidity, pressure, etc. etc. Let us look at this diagram and find out more. As you can see in the graph, the one bar is uncompensated and the other is compensated. The error is much higher in the uncompensated bar rather than in the compensated bar. So without reliable and accurate wavelength compensation, errors of 20 ppm to 30 ppm would be common in linear measurement readings when variations of temperature, humidity and pressure for nominal values are combined. These errors can be reduced by a compensation unit. The device measures the air temperature, pressure and humidity, then calculates the refractive index of air and hence the wavelength of the laser. The laser readout is then automatically adjusted to compensate for any variations in the laser's wavelength in machines today. The advantage of an automatic system that we use today is that no user intervention is required, and that compensation is updated frequently. So this is basically the error management which we can see in today's devices or machines. So that is all, and this was basically an overview of modern interferometry, and I hope you found the video enjoyable and informative. Thank you for watching.